So let me give a summary of the previous episodes. So in the first lecture, I gave the introduction and motivated what I'm presenting by open problems. I might come back to that in the end of that lecture. Think about conditional regularity for the Landau equation. And now we are looking at the elliptic case. Today we should be able to do the elliptic case and hopefully the whole modification necessary for the parabolic case. And the last lecture will be about the hypoelliptic case, but a lot of tools we'll introduce here already. So I now skip all the discussions about the Hilbert 19th problem and focus on the following theorem, which is what we are really looking for. So we have an open set of Rn and an H1 function that is solution to the following elliptic problem, where A is a symmetric, measurable matrix valued function, so that it is bounded above and below by multiples of the identity. And the whole goal is to prove that there exists alpha. You'll see what it is from the proof later on, so that f Hölder in u tilde less with a constant that depends on the u tilde to f L2 in u, and sorry, that would be for all u tilde open, compact included in U. Okay, so that's our statement. Here it depends on u tilde, so it depends also on the lambda, the constant of ellipticity, and obviously on the dimension. But this is universal beyond these dependencies. So that I've done already before, and I'm going to remind you, because otherwise it's really hard to see the structure of the proof, which will be the same in the parabolic and hypoelliptic case. So the first lemma of the Giorgi was the following. If you've not seen the previous lectures, just notice that the class star plus this assumption is invariant by scaling and translation. I'm not saying the equation stays the same, I'm saying this assumption stays the same. Okay? So the first lemma of the Giorgi is the following. Under the same assumptions, in fact, I told you last time already, in fact, secretly it's enough for f to be only sub-solution. So in fact, you don't need to assume the equality in the PDE, but it's enough to assume that it's non-negative. Then there is, we're going to use this statement, so that's why I'm recalling it. There is delta, so that if locally f is less than delta in L2 norm, then f plus, the positive part, f plus is exactly what you think it is, right? F plus in L infinity norm in B 1/2 is less than 1/2. It's the historical formulation. Of course, there is a lot of arbitrariness in the choice of names of the constant, but it doesn't matter. And the picture is that if you have a ball size 1 with very little L2 norm, then f will be less than 1/2 in the reduced ball. Okay? So that's the first lemma of the Giorgi. I explained why it's still valid for sub-solution. You could have a scaling invariant version if you normalize the measures you integrate against. And I discussed both the Giorgi and Moser version, which are very similar. And now let's go to the second lemma. The Giorgi 2, which is under the same assumption, but this time, let me emphasize that here f has to be a weak solution, not just sub or super solution. You need both one-sided notions at the same time. Then, so that has to be 0 here. And then you have the reduction of oscillation. There is a nu, so that oscillation of f on the ball 1/2 less than nu oscillation of f on the ball B2, where the oscillation means the sup minus the inf. Okay, so that's called the reduction of oscillation. It is implied, so corollary, I won't redo it. You get the Hölder regularity. Just because you can iterate this reduction of oscillation at a point. And this lemma the Giorgi 2 is implied by a lemma often called the decrease of the maximum. I will explain. Which itself is implied by the intermediate value lemma of the Giorgi. De Giorgi intermediate value lemma. And understanding that is the key. The intermediate value lemma is really where you measure the oscillation. Okay, so I've told you what is this. I need to tell you what is this and prove them. The lemma of decrease of oscillation, decrease of maximum, sorry. Goes as follows. Maybe before I proceed, in case you wonder, the initial statement is given in a general open set. All the other statements are given in a ball. It is due to the scaling invariance and the translation invariance. Once you know how to do everything in balls, you can do everything around any point of your open. So we never come back to the open set. We just work in balls. So, and this one has also another name. It's also called the measure to pointwise estimate. So here is the statement. Consider f less or equal to 1. Weak, everything is weak. I mean, I won't repeat it all the time, but the solutions I consider are weak. Weak sub-solution in the ball B2. So an H1 sub-solution in the ball B2, 2. So it is a sub-solution, so it looks like that. Okay, then with the usual, with A, symmetric measurable, and as always bounded as you want, as you expect, then we have the following statement. If we assume there is a mu so that, I'll make a drawing in a second, there is some negative values in a way you control and the ball B1, then there is lambda in 0, 1 depending on the usual suspects, dimension, lambda, but also your mu, so that f in the small ball 1/2 is less than 1 minus lambda. Okay, so let me give a drawing for that. By the way, all my supremum and infimum are essential, but a posteriori, since we'll prove that the solution is Hölder, they will always be, in fact, secretly defined everywhere. You pick up just a continuous function in the class of equivalence almost everywhere in the end. So the setting looks like that. Here, f is a solution. In fact, a sub-solution, sorry, that is less than 1. Here, you know that f less than 0 happens enough. I don't have a better way to say that in English, but I mean the statement is there, you see what I mean? Then, in that little ball, f will be less than 1 minus lambda. So will be secretly, strictly less than 1. So that means the satisfying the equation, and in fact it's the h1 bound that you get from the equation, will force the function to not go too high here because it's surrounded by enough negative values. Okay? So I have proved already, so I think last time I already did prove that, right? I think I did. So to prove that the decrease of maximum implies the reduction of oscillation, it's very simple. You normalize and the minus lambda reduces the oscillation between the infimum and the maximum. Okay? So now I'm going to state this one and prove that they imply, prove it and prove they imply each other. So that's the next step. We arrive at the core, really, the hardest part of the theory, the intermediate value lemma of the Giorgi. So this lemma is, in the elliptic case, independent of the equation. So there exists a constant c that depends only depending on the dimension, so that for any g h1 in the ball B1, no, sorry, it's even more general than that. Let me give the exact statement doing what we want. For any g function on B1 measurable, so that g plus is in H1 B1, then, so without a drawing it looks technical, but it's actually not very complicated. So I'm saying that the measure, the modulus means the measure of where g is between 0 and 1/2 is greater than this constant divided by L2 norm of the gradient of g plus squared. As always, the 0 case is not interesting, so I don't do zerology. And then the product of the measure of the upper and lower case. So the measure of g greater than 1/2 in the ball and the measure of g, sorry, and the measure of g less than 0 in the ball. squared. And in fact, I'll show you that the optimal scaling is not so hard to prove. Okay, so that means that's just saying I'm looking at the function of g defined in the ball. Okay, now look at the values of g, if it makes sense, if you want to visualize them like that. Right? This is the graph of g in some sense. So I'm saying that if I know there is mass here, I know there is mass here, there must be some mass in between, and I quantify it. If you were in the world of C1 functions, what would you do? You would just write down a Taylor expansion and say you have to go through you have to pass the bridge. And you would do that enough times. Well, we'll do something of that style, but it's an extension of the sort of trivial Taylor argument, but it's not a trivial extension, because we want to do that only for G in H1. And in large dimension, it's much less regular than C1, right? Okay, there are many small remarks on that. It would be enough, so another small remark. Okay, maybe I'll put down all my remarks here. Remarks 1, if G were C1, this is Taylor expansion, or the intermediate value lemma. I mean, the standard intermediate value lemma. Second remark, 1/2 here could be replaced with theta close to 1, which sometimes is useful. Proving such a slightly weaker statement is sometimes helping you, and the rest of the regularity theory would work. Still works for, still implies all the chain, still implies the other lemmas. So that is useful to know. Yeah, and the last remark, sometime you'll find in the literature that it's called the isoperimetric lemma of the Giorgi. So if you like to think geometrically, this is because we are bounding. So you could easily see that if you have a GH1 like that with G plus H1, you could collapse all that. You could define a new function. That's what I will do in one of the proofs. You could collapse this whole layer into just a line here. You could collapse this whole layer into just a line with some, charge, so with some measure. And then you're really trying to bound the interior measure by the measure of the boundary. So that is why sometimes it has this other name from geometry. Okay, so this is the most interesting part, I think, of this theory. So what I'm going to do, I'm going to prove this intermediate value lemma, and then give an argument for recovering the decrease of maximum. And you know already how to recover the reduction of oscillation, so you'll have the whole answer to the problem. So let's first prove the intermediate value lemma. And I'm going to give several proofs of the Giorgi intermediate value lemma, because all the proofs have something interesting to teach us. The first one is the most standard one, and the two other proofs were proposed in the last 10 years. The first one by Anceschi-Rebucci and the second one by Jessica Guerand. And they were really the motivation for what I will present in the hypoelliptic case. So the first proof is proof 1, non-constructive argument by contradiction. It's obviously less satisfying in terms of getting the constant, but you'll see that we'll learn something from it, which is that the statement is far from optimal. So it goes, I will just sketch it because I won't use it much later, but it works exactly as you think it should. You consider a contradiction sequence. So contradiction sequence GK so that the measure of GK between 0 and 1/2 is going to 0, right? I want to fail the theorem, and the measure where GK is less or equal to 0 is bounded uniformly, and the measure where GK is greater than 1/2 is bounded uniformly. Okay, so that's my assumption for a contradiction sequence. And
so there are other options to contradict the inequalities. I mean,
I'm not trying to be very subtle. You're right. That proof won't capture the exponents, for instance. That proof will prove something weaker. That proof will just say if these things remain positive, that one is positive in the end, which is nevertheless for the whole enough for the whole theory. What were you thinking about?
Yeah, I mean, maybe related to the exponent that one of maybe A2 can go to 0 and still the inequality is okay, or I mean depending on.
No, I'm just saying. This is my assumption. This is my conclusion. So failing it means assumption true, conclusion false. No. I don't think there is another way to contrapose it.
Okay, maybe, okay. Yeah.
Perhaps we also need to suppose that the L2 norm of the gradient is bounded.
Mm-hmm. Yes, that is, yeah, that would have been another way. That's true. I'm not, that is true. Good point. I forgot, actually. That cannot happen because of something I forgot to write here. I want GK so that the GK plus is bounded in H1. Thank you. Actually, that was very important. Right? And indeed, I could have thought about failing through the H1 bound, but that's not what I'm doing. I'm assuming the H1 bound bounded, and now I'm failing the conclusion. So with all these bounds, let's define the following thing, which does exactly what I sketched very badly in that truthful drawing. I'm defining G tilde K to be 0 when GK is less than 0, to be GK of X when GK is between 1/2 and 0 strict, and to be 1/2 when GK of X is greater or equal to 1/2. Now, you can check that, yeah, that's all the modification I want to take. You can check that then your GK tilde is bounded in H1, just because you assume your GK plus to be bounded in H1, and the 0 values do not matter. Okay, the gradient is always 0 at the 0 value for that object. So you have bounded in H1 uniformly in K. So now we take the heavy machinery and we just follow. There's no subtlety anymore. You use all the compactness you can. You have H1 bound, so by Relish quadrature theorem, you have strong compactness L2. You combine with weak compactness H1, and in L2, up to taking a further subsequence, you have almost everywhere convergence. So, up to renaming the sequence, if needed, right? I don't want to have multiple indices. we have that the G tilde K is converging strong to some G infinity, strong L2, weak H1, and almost everywhere. Okay, and now with that convergence, you see that yes, let me keep the intermediate value lemma. With that convergence, you see that G infinity is bounded H1, is the weak H1 limit of a bounded sequence, okay? And the almost everywhere convergence allows you to pass to the limit in the measure sets, and you get that G infinity is almost never between 0 and 1/2, and spends some time at 0 and spends some time at 1/2. So therefore, you deduce that G infinity secretly is just 1/2 of a characteristic function of a certain set, let's say B calligraphic, where B calligraphic is a Borel set in B1, that has measure strict positive and strictly less than the measure of the one ball. Right, you see it's a function that is always 0, 1/2. So it's a characteristic function. And I'm saying it's not always 1/2 and it's not always 0. And well, the proof is finished because the rest is a calculation you'll find that is very standard in many textbooks. Then such characteristic function is not in H1. So the moral of that is that, and if you look at textbook, what do you need for a characteristic function? You need HS with S less or equal, or the equal I forgot. Yeah, I think included. So the characteristic function will be into H up to 1/2. So you see that was my last remark. The statement would still be true with as an assumption G in H 1/2 maybe plus 0. Sorry, I forgot if the limit case is included, but what I mean precisely is that H1 is not optimal. The intermediate value lemma would still be true with a fractional Sobolev space. As far as I know, maybe there's some papers I don't know from another community framed very differently. I don't know a quantitative proof explicitly in the elliptic case like that. It's connected to some non-local proof in the hypoelliptic case, but I don't know a clean elliptic proof with that quantitative, I mean. Okay, so now let's go to really what is the goal of these lectures is to convince you that building trajectories is the way to really study all these regularity problems. So I'm going to give you a second proof. That was an interesting, isolated, intriguing remark in the lecture notes of Alexis-Vasseur, published in 16, but I'm sure it's a course he gave in Beijing before that. And it goes like that. So you're in the ball B1, and you consider G tilde X. you perform the same sort of shrinking, if you want, as what I did for each terms of the sequence. So 0, 0 for g less or equal to 0, g of x for g between 1/2 and 0, and 1/2 for gx greater than 1/2. Okay, so now that argument goes like that. There are regions, let's say, where g tilde is 1/2, right? So that would be this region. And there are regions where g tilde is 0. They are just measurable. They can be crazy sets. And in between, well, we are here. I'm going to pick up points and look at the trajectory between the points. Okay, now you'll have to imagine, because the case is very simple, but I guess it's good to start with something simple. I want to use a trajectory generated by the vector fields that generate my second order operator, which just happen to be all the dxi. So the simplest trajectory I can do is just a straight line. Okay, so here at that level it will look pretty stupid, but that's the thing to do. I'm just writing a trajectory like that, and now I want to do a sort of average form of the Taylor expansion. So I'm going to take, following my picture, x in, yeah, that's consistent with the picture, I hope. X in a region where g is less than 0, the blue region, y in the region where g is greater than 1/2. And now I'm writing 1/2 is equal to g tilde of y minus g tilde of x equal, and now I write down a Taylor expansion. Everything is justified a posteriori by density in H1, of course. The only, what matters is that in the end of the day, my estimate only depend on the H1 norm. And I just Taylor expand. Right, okay. So now the left-hand side is bounded by the right-hand side, and I will bound the right-hand side a little bit better. So there's a little bit of a clever step here due to Alexei that allows to grab the optimal scaling. Afterwards, I'll give you the argument of Jessica that is way simpler but doesn't get the optimal scaling. So 1/2 is less than, I can just reformulate it like, yeah, I'm just doing a little change of variable, but it's the same thing. I put the modulus inside, and here I have x plus s. I've done a small obvious change of variable, like that. And now, in order to avoid having this upper bound, I'll just want to integrate over the whole half line, but I'll keep track of because I know this segment is inside my ball B1, I can always include here for free the characteristic function of that in the ball B1. Right? At that level, it's trivial because we are in the ball B1. And now I just bound from above. I get integral from 0 to plus infinity, g tilde, and then I have this. And I have the characteristic function, which I don't repeat. And now I integrate both sides. First in y, So y has to be integrated in all the red parts. On my drawing, right? So I get 1/2 times the measure of that red part less than, and here I have an integral of y on that red part, and then an integral, line integral like that, and then I have my characteristic function that will prove useful later. Okay, so now the idea is that at that level I'm just going to drop that, saying it's less than the whole integral of f in B1, and I'm going to break y with spherical variables and reconstruct a new spherical variable here. Okay, let's call that z. I want to reconstruct, what do I want to do? I want to reconstruct a full integration variable z from S and a part of y. So it's not very complicated. So I do a change of variable of y around x plus r sigma, okay, change of variable, and I get that my left-hand side, so the area of my red zone, 1/2, is less than, so I have the radial variable r to the n minus 1 dr. Sorry, not up to plus infinity, that would be a problem. Up to 2. Why 2? Because y lives in a ball B1. So whichever point I take as a center for y, the maximal length it will travel will never be more than 2. Right? The diameter of the ball B1 is less than 2. So I will never get more than 2 on the radial variable. And then I have my angle, and I have S x plus S sigma, characteristic function x plus S sigma in B1. Okay? So that I integrate. So I get, what is it, 2 to the n over n, right? And then the other one, I just perform a change of variable, that is z, backward. And I get integral of z where? Well, I have this characteristic function that forces z to be in B1 of gradient g tilde of z. And of course, I don't have the Jacobian I would expect from the spherical change of variable. So I have to pay a price, which is z minus x n minus 1. So I have traded my estimate for a singular integral. And now I integrate in the blue zone. Yeah, it's still there. So we integrate x in the blue zone to get that 1/2 of the product of the measure of the blue zone and the red zone is less than, so I collect everything I had there, so 2n over n, and then I have an integral of x over b1 inter where g is less than 0, an integral of y in B1, and then, it's not called y, so it's called z now. Like that. Okay, so now it's done. You would lose the optimal scaling if you don't. You could drop that and still get a result. But if you keep it and do a last little clever step of rearrangement, you get even the optimal scaling. So now by Fubini, you first integrate in x, and you observe that. So the integral in x in this weird set of dx norm z minus x at minus 1. What is this? Well, it's very easy. This is a this is a decreasing function radially around x. So you can always rearrange your set around. Did I say around x or around z? Right? You can always rearrange this set around z. And I can say that it is less than the integral over BR naught of dx over x. You can call the new variable x tilde if you want, to emphasize that I've done a change of variable and rearranged, where R naught is so that the ball has exactly the same volume as your initial set. Where the ball with radius r naught is the same measure as the blue set. Okay, so well, we integrate that now. So we obtain that this quantity is less than that, which is the integral. So there is a constant, which is the spherical, the volume of the sphere, of course. I'll drop some constant in a second anyway. And then I have integral from 0 to r naught of dr. So I'll get exactly up to a constant depending only on the dimension r0, which means simply the measure to the 1 over n, sorry. Okay? If the volume of the ball is equal to this, it means the radius is like this to the power 1 over n, because we are in dimension n. And then we just go back to that inequality, and we get that the product of the two two measures is less than, there is a constant depending on the dimension that I don't want to write, and then there is the integral in x here that I've just calculated, and the integral in z is what remains. So I have that 1 over n times the integral in z over b1 of that. Okay, we are almost there. So that I could simplify with that in dimension greater than 1. In dimension 1, there's nothing really to prove, so I was not considering this case. And now you just observe, and we'll reuse that a lot, that the gradient of g tilde is 0 when g tilde is 1/2, g tilde is 0. Why is that? Because they are respectively always local maximum and local minimum. G tilde is always between 0 and 1/2. So therefore, this last integral, in fact, is the same as the integral in the intermediate zone. And now we apply Cauchy-Schwarz to get that it's 1/2 of the measure of the intermediate zone, power 1/2, times the L2 norm here, which is what you saw appearing in my theorem. And this concludes the proof. So it's easier for you. My statement is no more on the blackboard, but you have it in your notes. So now this measure, you put that on the left-hand side. This measure controls below the product of these two measures, and you have to remove this factor from here. That's what gives the 2 minus 2 to the n. Okay, so now that argument is very nice. However, we were not able to extend the rearrangement argument in the middle of Alexis later on to the parabolic and hypoelliptic case. Alexis' argument, as far as I know, was never extended even to the parabolic case. So everything I will present on trajectories was also new even in the parabolic case. So one of the questions after in the end of the PhD of Jessica was to obtain a quantitative proof in the parabolic case. And that's what we worked on when she came to Cambridge for the postdoc. And she had come up with a nice remark on the elliptic theory, 2018, I think. She gave a simpler argument that replaced more or less part of the argument of Alexis by the Poincaré inequality. So it's less sharp, but it's very short. And what we'll do in the parabolic and hypoelliptic case will be to combine that and add new layers, but they are both inspiration for what we do. So we define G tilde as before. And the first step is to recall the Poincaré inequality in L1. Okay? So we have that integral in B1 of G tilde minus average of G tilde in B1. So I'm using the standard notation for average, right? Integrating G tilde and dividing by the measure of the set is less or equal with an absolute constant, the Poincaré constant, the L1 Poincaré constant, to integral on the ball of gradient G tilde modulus. Okay, so the Poincaré inequality is a sort of integral way to measure oscillations. I'll come back to that when I'll explain the arguments of Moser. And then the key remark is the following. If we look at the red zone, the measure of the red zone on my drawing, which let's say I normalize by B1, just by Chebyshev, that is less than, and I've got a factor 2 walking around, yeah, it's here. It's less than that where I do integrate G tilde. G tilde is non-negative, don't worry about modulus and so on. Right? Because when G is greater than 1/2, G tilde is 1/2, so I can always bound the measure where G is greater than 1/2 by twice the integral. And I divide by B1, so it is exactly twice the average. Now, if I do the product of the measure of the blue zone and the measure...
So there's a square? Ah no, Poincaré L1.
Ouais. It's very important to do it in L1. There are several other papers in the series we wrote where we really use it in L1 because later we want to take advantage of Cauchy-Schwarz to extract a measure of a set here. So we really want to start working in L1. It's important for the argument. So the product of the measure, well, I just use that, is less than twice over modulus B1. Sorry. Twice, what am I doing? Did I put the B1 correctly? Yes, sorry, I put the B1 back on the right. So there would be the average, and there would be this term I've added. This term, I can always write it as the integral of the set. That's a triviality, right? So this term is just the integral on the blue set. The integral of 1 on the blue set. But I have the average as well. So I can always say I integrate this average, which actually is constant on the domain of integration. Okay? I'm doing nothing at the moment. It's just manipulations. I've bounded that by twice the average. And now the product of the measure is less than, well, some constant, the integral on the blue set of a constant, which is the average of the function. But now, on that domain of integration, you can arbitrarily change the integrand by adding g. So you deduce that the left-hand side, the product of the measures, is less than twice the measure of B1. And then I have, so on that set, when g is less or equal to 0, g tilde is 0. So I can always write it like that. Why? The average is positive, non-negative. Okay, so average and modulus of average is the same. But g tilde is 0 on this domain. So I can always add arbitrarily g tilde inside the modulus. Okay? And now I drop the restriction on the domain. Integral B1 g tilde minus average g tilde. And I now apply the Poincare inequality. So I put that in a constant as well, and I get integral in B1 of g tilde. And you can observe that now we have already arrived directly at the last step I was in there. I can apply Cauchy-Schwarz to get, for the same reason as before, the gradient is 0 at 1/2 and 0 at 0. So I get, by Cauchy-Schwarz, half of the measure, power half of the measure where g is strictly between 0 and 1/2, and the L2 norm on the gradient. Okay, and that concludes the proof. You have a bound between the measure of the intermediate set is bounded below by the product of the two sets. Okay, so we'll heavily take advantage of that simplification in the argument. One small remark, I'll come back to this. All this intermediate value lemma relies on a regularity only. So if you look at the literature in the elliptic parabolic case, you might be surprised I recall the equation all the time. In all the lemmas, and it's true as well in the parabolic case, remain true when replacing the equation. You replace the PDE by the infinite family of energy estimates. Just a warning, I'm not saying you replace the PDE by H1. The infinite family of energy estimates is more than H1. Do you see what I mean? It's an infinite family of inequalities relating L2 to H1 with an exact scaling coming from the cutoff function. And that is called the De Giorgi class. So you have De Giorgi classes in the elliptic theory, the De Giorgi classes in the parabolic theory. In the hypoelliptic case, it's not so clear, because the energy estimates do not capture the full regularization in all directions. Okay, so the last proof I can do, and then I'll do the parabolic case after the break, is the proof that the De Giorgi intermediate value lemma implies the decrease of the maximum lemma. That's the last step. With that, you have the whole proof of the De Giorgi theorem and therefore the Hilbert problem. So this is a finite induction due to De Giorgi. Let me just show on a picture. So this is a representation of the values. Did I call F or G? F. So this is a F solution F, and I represent the values of F. F is less or equal to 1. The idea of the Giorgi will be to have an iterative scheme where you cut only a layer closer and closer to 1, and you redilate it to make it 0, 1. Okay, so that's all. And he says each time, if you have not reached a moment where the L2 norm is small enough to apply the Guerand-M integrability and decrease a little bit below 1, then you continue. And you can't continue forever because the intermediate value lemma says every time you have to do it once more, you add a little bit of measure in between. So you'll see in the calculation, and that reaches an absurdity if you don't stop. I mean, it looks like a contradiction argument, but it's explicit because the moment you stop is quantitative. So let me try to explain intuitively. The full calculation maybe is not the most interesting, but the intuitive explanation is the following. Yeah. So we assume in B1 that f is less or equal to 0 enough. You remember? So f spends part of the time below 0. F is a solution on B2 that is always below 1, B2. And I remind you the goal, yeah, it's not written anymore. The goal is to prove that actually f on a smaller ball is strictly below 1. For some lambda strict positive, it's less than 1 minus lambda. Okay? So the iteration, the finite iteration goes like that. So I said solution, actually sub-solution is enough, sorry. And you'd have a symmetric theorem for super-solution when you increase the infimum. So you define for k greater than 0, G0 is equal to f, and Gk in general is 2k f minus 1 minus 2k. 2 to the minus k, sorry. Okay, so it looks technical, but this is the cutoff. This is the line that is closer and closer to 1. Okay, and I'm going to take the positive part of gk. So by putting the cutoff higher and higher, I'm cutting everything below this thin layer close to 1, and I'm zooming it so that the values still span 0, 1. Okay, you can check that gk is always less than 1. It's made for that. It starts with being f, and you can also check that there's a very simple induction relation. Gk plus 1 is equal to 2 gk minus 1. Okay, so now gk is a subsolution. Why? Because it's just f plus something times something. The equation is linear. Therefore, we discussed that last time. You can apply convex function, and by approximation, the positive part works. Gk plus is a subsolution. So for all k, we have a subsolution that is below 1. Now, other remark, f less or equal to 0 always imply gk less or equal to 0. Just look at the formula. So therefore, we have that the measure of where gk is less than 0 greater than the measure of where f is less or equal to 0 is greater than this mu for all k. Okay, I think I've stated all my conditions on this little iteration. It's a very simple collection of zooms close to 1. And now, so now this is the part, the intuitive explanation. If we had that the L2 norm of f plus was less than delta square, that's the square of the L2 norm, sorry, so that's why I put a square here, with delta small enough, according to the first lemma of the Giorgi, so the delta would satisfy the first lemma of the Giorgi, then we would deduce that sup of f plus in B1/2 is less than 1/2. And we are done, we'd be done, with lambda equal 1/2. Of course, it's not always the case that we have that. So, in general, let's say k naught, at least 1. Let's pick up a k naught so that for all k between 0 and k naught minus 1, we have, and that is just g0 plus, sorry. So that's the beginning of my iteration, okay? F is just g0. So now, if it's true the first one, we're done. If it's not, let's pick up a k naught so that it's not true until that. So I'm assuming that for all these indices, I have that this is greater strictly than delta square. So let k naught like that, okay? And now I want to prove that k naught is bounded. Meaning, if I found a bound on k naught, I know the next one, k naught plus 1, satisfies the assumption, and I'll conclude. And the bound comes from the intermediate value lemma. So, why is k naught bounded? And then, because of the intermediate value lemma, I combine, let me put some colors if it's still written somewhere, I hope. No, it's not there. Where are the properties of my iteration? Yeah, they're here. So you combine that with that. And you have that for k, let me try to get the, for k equals 0 up to k naught, it's important to get a -1 here. You'll have that the measure of what used to be my red zone is equal to, so the red zone for k is just where the next one is greater than 0. This is due to the way they are constructed. Okay, they're just refolded and re-extended. When one element is greater than 1/2, it means the next one is greater than 0. So that is greater or equal to this L2 norm. And because I made an assumption that, okay, oh sorry, this one is up to k naught, that's it. I knew there was something dodgy with my indices. And now I'm testing up to k naught -1, and that one is greater than delta square. Okay, so now you have two assumptions on the measure, the two red circled assumption. We have exactly the setting for the intermediate value theorem. The intermediate value theorem of the Giorgi tells you that there is alpha so that the intermediate value region is has measure greater than alpha times B1. And that's it. Now you just observe that the measure where G naught, the last one, is less than 0 can be, if my drawing is still there, I hope so, yeah. Now I say that I go up to the point I stopped and I calculate the measure by summing all the layers. So that one is greater or equal to B1 inter G k minus 1 less than between 0 and 1/2, and it's a lower bound because the sets are disjoints. So I'm exactly unfolding that into two parts. And then I will re-unfold that one into two parts. This one is greater than alpha B1. But that one is exactly the same I started from, one index below. So I continue, and I get exactly k naught alpha B1 plus the first one, and when I reach the first one is just G0, which is F. I mean, let's call it G0, but okay. And this is greater than k naught alpha plus mu mod B1. Okay, we have a lower bound on that, and that's it. The argument is finished because we deduce that the left-hand side has measure less than B1, obviously. So we deduce that. So we get k naught less than alpha minus 1. That's clear, right? I mean, I'm losing a bit. I'm not using mu, but that's it. And that concludes the proof. So then for the next one, we have that, which implies that, which implies supremum of g k naught plus 1 less than 1/2 on the smaller ball. That's the first lemma of the Giorgi. And that means exactly, the conclusion here means exactly supremum of f. If you look at what the gk naught plus 1 is, supremum of f on the ball B1/2 less than 1 minus 2 minus k naught minus 2. And that's our lambda. Okay, so we can make a pause here. I just make the remark that I hope I'll have more time to talk about that in the fourth and last lecture. You can see that here lambda behaves like 2, so an exponential, constant exponential minus another constant, and k naught which behaves like that. And then if you, I try to follow it even more in the notes. You could continue to track down in cascade from all the proofs, now that we have solid, robust arguments at every steps, and you'd find something like that, where lambda was my initial constant of ellipticity. I just wanted to emphasize here that there is a double exponential structure that will start appearing in this. So the constants are very, very bad. Okay, so we can stop maybe for a few minutes. So in this second part, what I will try to do is to explain what are the ideas of Moser and Kruskov that followed. My experience, the last time I taught part of this course, much less because it was shorter. That was the part that was interesting people most because it's not covered usually in lecture notes. So I'm making a detailed comparison with the argument of Moser and Kruskov in the elliptic case, and then I'll go to the parabolic case. In the parabolic case, I won't redo everything. I'll just point out the differences to what we just did.
So could you please give the detailed reference for the Kruskov paper?
Yes, absolutely.
Because there are many, there are a couple of papers of Kruskov.
Absolutely. This is Kruskov. The one I will be talking about exactly is Kruskov 1963. He was working visibly on it. I don't know, I've never met the guy, of course. He visibly was working on it exactly at the same time Moser was trying to understand the papers of Nash and Giorgi. And it's a paper called A priori bounds for generalized solution, like weak solutions. It's translated from Russian, of course, so it's not fully reliable, of second order, the terminology, second order, elliptic, and he does both in the paper.
And you found a version that's been translated in English?
Yes, I think so, because when we looked at it with Cyril, yes, we had a version in English. And the argument of Kruskov, in some sense, it came afterwards, so it would be unfair to Moser to directly jump to it, but it's by far the shortest argument. It has this beautiful flavor of clean, short Russian paper that makes you really think when you read them that the problem was actually trivial, because the proof is so clear and short. Okay, so the program first, Moser and Kruskov ideas in the elliptic case, and then all the changes you have to do in the parabolic case. So first, Moser's method. So here we are talking about two papers because François was asking about it. So they are papers of, so in 1960, Moser was redoing another proof of Giorgi's original result. The title is actually that, a new proof of Giorgi, blah, blah, blah. And in 1961, he gave the proof of the Harnack inequality for elliptic PDEs with rough coefficients. So let me explain the idea. So Moser was heavily influenced by both Giorgi, the Giorgi paper of 57, and the Nash paper of 58. And in particular, in the Nash paper, there is the use of the integral of the log f log f. You know, Nash differentiates that in time and uses what we now call the Nash inequality. I forgot the name. The inequality that interpolates between the gradient and the L1 norm. The L2 between the gradient and the L1 norm. Anyway. No. The inequality where you interpolate between L2 between H1 and L1. The Nash, just Nash inequality. Yeah, okay. Which actually is not invented by Nash, because he says in this very paper that it was communicated to him by Nirenberg or something. But anyway, so he uses the log here, and that's very well known. Most papers talking about Nash paper have not looked more than that, I suppose, because it's in the 2 first pages. But Nash, the core of the proof of Nash is something he calls G-bounds, which are certain integrals on the log of the solution on certain subsets with certain weights, with a collision of scale, which I will come back to, which is very apparent in the Kruskov viewpoint. If you want, I'm not covering it at all in these lecture notes, but if you want to look at the proof of Nash in a friendly written way, because the paper on Nash is short, but it's not so easy to read, at least for me. You have a beautiful set of lecture notes by Camillo de Lelis called The Masterpieces of John Nash, which he wrote for Proceeding of the Abel Prize. And one section is an entire rewriting of the proof of Nash, clean and fully checked and very nice. Okay, so Moser is influenced by that, so he wants to use the log of the solution. That's the core idea. And that's one thing. He wants to use the Poincaré inequality, which made already a guest appearance in the argument of Jessica, in what I presented. He wants to measure oscillations by integrals rather than pointwise. That's the core idea in Moser viewpoint. And he wants to take full advantage of the Giorgi first lemma true for sub-solutions. Okay, so we'll put all these ingredients, and here is what was the original argument of Moser in the elliptic case. So Moser defines something like that. You'll see why in a second. The normalized integral of f plus p norm. And he looks at that for p, anything on the real line, and r strict positive. Okay, and now the argument of Moser is that, of course, as I told you already in the proof of Moser by the first lemma of the Giorgi, you have the power bigger than 1 of f sub-solution, so you can do the energy estimate. So Moser starts by proving a sort of version of the first lemma of the Giorgi on steroid, which proves the following, that this, which is just the infinity norm, right? That's just a notation for that, less than this for p strict positive. So that is just, for the moment, a pedantic way to rewrite the Giorgi first lemma, except that Moser observes, I mean, it's super easy to do, but it observes that you can actually go below L2. You can go to any integrability by a strict positive exponent. It's not very hard. I don't want to do it now because we would lose time, but it's a small further iteration. And using that the negative powers of f will be super solutions. So, you inverse the way and you can do still estimates on them. He also proves the following. You have that is less than this. Okay, I know I'm not doing that because of lack of time, but you have to believe me, these are sort of more intricate, sophisticated version of the first lemma of the Giorgi. There are inequalities between L infinity norms and LP norm for p less than 1. Okay, just on f or on 1 over f. That's the moral of that. And so, if you can relate that to this, okay, that of course I will talk about that in a second, then you prove something that is even better than the Hölder regularity. Then you obtain that, no, sorry, I wrote it the wrong way. No, yeah, the right way, sorry. Yes. Oh, so of course, sorry. I had to inverse the inequality because, sorry, 1 over f is a super solution. Nobody protested, okay? This one goes the other way around. And so if you can relate the middle step, so it's a very beautiful argument. Unfortunately, way too complicated in many applications. The Giorgi method remains way more robust. But conceptually, it's beautiful. Moser says you take all the powers, and I want to relate plus infinity to minus infinity. And unfortunately, I have to jump across 0. And you see, now you have that less than that, that less than that. So if you can relate that and that, you deduce this inequality. And that is just supremum of f plus on B1. Yes, I put the plus. And that is just infimum of f plus on B1. And that is called the Harnack inequality. The constant here is universal, so it doesn't depend on the solution you're looking at. And I'll show you in a second why the Harnack inequality is way more powerful than Hölder, but for the moment, how do we conclude? So the problem in Moser argument is really to prove that. That is the part that is more than the first de Giorgi lemma. In some sense, that is the part that is the equivalent of the second de Giorgi lemma. And to prove that, Moser proves that the log of the solution is bounded as bounded mean oscillation. It would allow to conclude by a result of John and Nirenberg, published in the same issue of CPAM. The result of John and Nirenberg tells you that if f has a BMO bound, then you have something like that. Okay, I'm obviously not going to prove that. I can do all the steps in this proof because it's, as you'll see, it's an extremely clever argument that is extremely hard to apply in practice. That is a result that's interesting in itself. F must have a BMO bound. It means, I will write it in a second, it means F is always quite close to its average. And then you have that, and now you remember that F, here you have a potential power, sorry, for some epsilon. You remember F is log little f, and then you have exactly a connection that I was searching for here for small p. Okay, you just plug Capital F is the big little f logged. So ultimately, thanks to this result, Moser reduced the problem to establishing a bound on the mean oscillation everywhere in the domain. And he proves that you can apply the John-Nirenberg result thanks to the following inequality. For any ball in your domain, in your global domain, you have on the log of the solution this bound which is universal. Universal means the constant depends on nothing. There's something that is really shocking in this bound, and I like to present that argument because it really makes understand somehow that in the Giorgi-Nash-Moser theory, at some point you create something from nothing. Because this bound has no right-hand side depending on the solution. It's the first bound I'm writing that is not a linear relation between anything. This is for free. The log of the solution is actually enjoying a BMO bound that is universal, always. So where does it come from? In fact, it comes from the fact, so you first prove a universal bound L2, that is just because you have basic bounds in your problem, that is easy, but not L2 removing the average, right? It's a pure, that's in the style of the first de Giorgi lemma. There's nothing really to do here. And then the energy estimate will tell you that the gradient on a ball is of a size r minus 2 of the ball. The r minus 2 comes from the derivative. You don't have a choice for that. It comes from the cutoff function in our calculation of the energy estimate. And finally, you apply Poincaré inequality. And in the Poincaré inequality, the diameter comes up, so it kills that term. Okay, so I need to explain why we have that. And this is perhaps the most important aspect of...
Sorry, here you're always talking about capital F being the log.
Yes, otherwise I don't have the box here. Because this box is again a universal bound from nothing. And the universal bound I'm going to write is the key to the proof of Nash, to the proof of Moser, to the proof of Kruskov. It's also the key to the proof of the Lie-Yao inequality in elliptic theory. It appears everywhere. It's the following argument. If you take a solution to an elliptic problem, or it works in the parabolic case as well. So F satisfies, do I need super solution, sorry. Right? Yeah, positive super solution. Then I consider what happens to the log, right? And you can check that. I hope I put my sign right. It's not a very easy way for you to decode it. Let me just expand that. If I expand just that thing, what do I get? I just get that, right? It's the gradient of the log. Now I've got two terms. One is just 1 over f, my original term. The other one is minus af grad f over f squared. Okay, now the point is that I can put that on the left-hand side, because here you can recognize, using 1f for each gradient, that it's actually a grad capital F dot grad capital F. I can recreate something depending only on the log. So I have simply that less than 0. Okay, you're all okay with that. I started from that and I obtained that. Now this is controlling from below the gradient of capital F square. So now you just need to integrate that against a nice test function. You have universal pointwise bound on F. And, oh, you don't even need, sorry, no, you need nothing. Let me do the final calculation. What do you get? You integrate that against the test function. Squared. You get that is less than so for the other term I do one integration by parts, minus minus, so I get a grad capital F, and then I had grad what did I call it, phi, and I have a 2. So far so good. Now I just apply Cauchy-Schwarz and I have integral mod grad f square phi square 1/2 integral grad phi square. And there is the ellipticity upper bound. Yes. Now the left hand side is controlling from below lambda minus 1 that. You can simplify the 1/2 power here. And you see, you simplify 1/2 power, and you get simply that you get 4 this. That is really the shocking estimate that is at the core of all these approaches: Nash, Moser, Kruskov, Li Yao, and so on. So you see, it's a universal bound from nothing. The right-hand side doesn't depend on the solution anymore. It comes from the collision of scale. It comes from the fact that this term is quadratic in the log and this term is not. Ultimately, that's where it comes from. So from that bound, Moser obtains a universal bound on the gradient. This comes from tracking the phi localization function. You combine with the Poincaré inequality in L2, it gets a universal BMO bound like that. And by John and Nierenberg, it gives the missing link. Okay, so now we have the argument of Moser. Why is Harnack inequality stronger than Hölder? Let me do it once. I won't redo it each time. It becomes a little bit more complicated in the parabolic and hypoelliptic case because of time, but it's not that different. So Harnack implies the reduction of oscillation. Okay. So if you have the supremum on my ball B1 less than a constant, let's call it CH Harnack constant, infimum F plus on the ball B1, what you can do, so if you remember how I stated my reduction of oscillation, I normalized everything. right? So I'll just do the same to make the proof simpler. So assume normalization as in the proof. And then, so you have G, so this is the G on which I want to show the reduction of oscillation. So my G is between 1 and -1 on B2. You remember, it is a solution, and they are attained exactly. And the oscillation of G on B2 is exactly 2. I don't know if you remember, I had divided, normalized everything so that my function was exactly saturating -1, 1. You can reduce to that in the proof of reduction of oscillation. Then you apply, so you apply Harnack inequality, which of course you can prove it also in the ball B2 and B1/2. You apply Harnack inequality. The constant would be slightly different, but you can take the worst of the 3 constants. That's no problem. You apply Harnack to 1 minus G, which is positive in B1/2, and you apply it to G plus 1, which is positive in B2 or B1. No, in B1/2 as well, sorry. Okay? So I assume I have that for all the solutions. And here I have 2 things that are already positive, so I don't need the positive part. Okay, and then I apply Harnack twice. So let M0 be the inf of G on B1/2, M1 to be the sup of G on B1/2. And now my 2 Harnack inequalities give me 1 minus M0, which is the sup on B1/2 of 1 minus G, less than Harnack constant the inf 1 minus G on B2, which is on B1/2, sorry, which is simply Harnack constant 1 minus M1. And similarly, 1 plus M1, which is the sup on B1/2 of 1 plus G is less than Harnack constant inf 1 plus G B1/2, which is just the Harnack constant 1 plus M0. If you sum these 2 lines, you just get that M1 minus M0 is less than Harnack constant, so it's giving you the result. It's less than 2 times Harnack minus 1, Harnack plus 1. So that is the original oscillation. That is the reduction that is strictly less than 1. So we have proven that is my new. Okay, so the Harnack inequality implies the reduction of oscillation and implies Hölder. You don't need necessarily Harnack inequality to prove all that. It's stronger. Now, what about the Kruskov argument? So Kruskov argument is going even further in taking advantage of the key G bound in the Nash proof. So he wants to extract even more from the equation on the logarithm. So you remember the equation on the, it's still written. Yes, I have it. So he wants to extract even more from that. So Kruskov directly proves the decrease of maximum lemma. Well, he proves it in the symmetric form, which is increase of the minimum. On some f, it would prove you would go back to the initial lemma I gave you on 1 minus f. Okay, so that would be exactly what you would prove what I gave you by looking at 1 minus f. So what does Kruskov does is so he considers f non-negative. Remember, for us in the decrease of maximum it was f less than 1. But for Kruskov it's f non-negative. Super solution. Remember, for us it was sub-solution. So he has everything is symmetric in his statement. In H1 of B2, solution 2, super solution to, well, my elliptic problem. And therefore, the log will satisfy what I wrote there. Now, Kruskov wants to make life easier, so he does cut off everything. So he defines. So the following function will do cut off at value 1 to avoid having problems. So minus log z plus z minus 1. Characteristic function z less or equal to 1. And this is for z strict positive. Okay, so what he's doing is he wants to cut off here, and he adds that to make sure when you differentiate you have no problem. Okay, this is obviously negligible for small z, right? But he wants to have no discontinuity and no discontinuity of the derivative. So I hope you'll find the Kruskov argument beautiful, because it's really 10 lines. And it shortcuts, well, even the Giorgi argument that's pretty short is completely shortcut by this argument. So, and it's quantitative as well. So the G satisfies, check it, the G prime is just z minus 1 over z characteristic function. G second, well, is simply 1 over z square characteristic function. And you have that. So what is G? G is a function that is decreasing, that is convex, right?
Just this is a multiplication or a plus? This is
what did I do?
1 times log z or?
Times by what, sorry?
Plus log z. The capital G.
Capital G is equal minus log z plus z minus 1 times the characteristic. So if you differentiate, you have minus 1 over z plus 1, yes, which is exactly my z minus 1 over z. And then you have this one. And you don't see the Dirac at that level. Of course, you would have a Dirac for the next step, but I don't go further than that. So it's a nice decreasing convex function, so that that's the clever idea. I mean, that's more or less what I was talking before, the collision of scale. He makes it even more explicit here. You have G second greater than G prime squared. Right? On our domain. And now the new unknown we want to consider is the following. So first, I have my F, you remember, super solution non-negative. I first lift it a little bit. And just to make life simpler, so I lift it by a delta. And just to make sure it crosses 1 at the same time as F, I will just normalize by 1 plus delta. So let's call that F index delta. And my new unknown is little g is equal to my transform capital G of JF delta. Okay, I'm done with all the formulas. So it's a little bit technical, but what I've done is just to lift a little bit. That's just a rescaling to see easily, but the cutoff is still at 1. Lift a little bit and then taken a log, but I have made sure my function cut off in a smooth way at 1. Okay, so now we have F super solution, and we look at what is the equation, the inequation, sorry, we obtain on this little g. So here the calculation is very similar to, well, maybe I have to do it so, to convince you. So that is non-negative. That is exactly, by definition, each little g is yeah. Yes. So that's the first remark. Okay, why do I have that? Just observe that g second is 1 over f squared. Okay, so the little g is just g prime. Maybe I should have written. What do I have here is g prime z taken at f delta, a g f delta, f delta. So there must be squared. There must be an inequality, sorry. Okay, and I have this. So it is less than g second f delta, a f delta, f delta. And now I'm adding plus g prime f delta the equation on it, because that is non-negative, that is non-positive, so non-positive. And I obtain that it is less than the full second order operator on g of f. Okay, so that is the little g. So little g is still a super solution. And of course, we'll be able to have a control on that as well. We still have the same inequality Moser was using. Okay? So the proof is more or less done. The main problem, the main difficulty is to define all these formulas. So now you take a cutoff function smooth that is 1 on B1 and that is 0 outside B2, and you have you integrate my equation that I just wrote here. By equation I mean the inequality between this and that. Okay, maybe what I mean is really that star. That less than that. I integrate it against this phi squared. And I get exactly in the same way. I mean, I've done the calculation for you just before with the Moser argument. It's the same thing. I will get grad little g L2 in B1, where this is 1, squared less than I feel I'm forgetting one estimate, sorry. No, that's fine. Like that, and now I test what is this. So be careful, observe that the collision of scale again. So here I have less than lambda squared g, so the maximum of the g is when it is when the argument touches 0, because it's a log at delta 1 plus delta, so the worst value is this. And this is less than ellipticity value log of delta. Uh-oh. Ah, no, okay, I'll just take 5 minutes to finish this argument. So, now I want to use that in order to, I want to relate that to the L2 norm. So, the goal of the rest of the argument will be to say, I will apply Poincaré, use the measure condition I started from to control the L2 norm, and then from the L2 norm I'll go to the L infinity norm by the first de Giorgi lemma, and I will relate something that will collide with this because of the power, because this is squared, this is the power 1, and I will end up with a collision of scale that will produce the bound. So let's do this. The first remark is that f greater than 1 is equivalent to f delta, which is f plus delta 1 over 1 plus delta greater than 1. So which is equivalent to g of f delta equal to 0. You remember, g decreases at 1. G is a convex decreasing function. It's 0 after 1. So then it means that if I do the average of little g on the ball B1, so the little g is the big G of f delta, well, this is the integral where f is strictly less than 1. Less or, yeah. When f is, yeah, strictly less. Otherwise, it's 0. Otherwise, I have nothing to integrate. Yeah. And then what I'm saying is that because of my measure condition, and I really hope it's still written somewhere, Kruskov method. Oh, yes, I've never written. I'm very sorry about that. Sorry, Kruskov needs to assume. Did I write it somewhere? No, I've never written it. Sorry. Oh my God. So I have to assume, of course, in the Kruskov argument, that there is some mass above 1. Did I call that? You remember this is the same in the decrease of the maximum. We assume there was some mass below 0. So in the Kruskov argument, you need, of course, the same assumption. Sorry, I forgot to write it here. And that's it. Now, look at my average. Because that set is never more than 1 minus mu of the total set, because of that condition, I get by Cauchy-Schwarz simply that it is less than root of 1 minus mu, and then and then the integral of the L2 norm. Okay, so now because we know that the average is always less than the L2 norm with a constant strictly less than 1, we can deduce that by orthogonality, if I look at the full L2 norm, it's it is less than the L2 norm plus the average. Okay, will you be okay if I write that the integral divided by the measure? Okay, so just by orthogonality, it's the same as this. Standard, right? And now I'm using that argument to deduce that this is less than, this one is less than 1 minus mu this. Just because we wrote, that's exactly what we wrote. Here I have a 1/2, of course. I put it in the other side, and I obtain, I'll finish the proof here. Okay, so you put that back on the left-hand side. You have mu times that, and you divide by mu. So you obtain that the L2 norm is less than, with a certain constant, 1 over mu, and then the L2 norm without the average. Now you apply the Poincaré inequality in L2, and you get the gradient, the norm of the gradient, and you just now bound this by the argument we just did. I hope it's still written somewhere. Yes, it's just there. Okay, the previous line, previous estimate. Okay, so now on the left-hand side here, you can use the De Giorgi first lemma because you have my G, which is here. Yeah, you have the G, which is here, which is a subsolution. Oh, sorry, I said super. What's complicated in the Kriskov argument is that it does a lot of transformation. So that is greater than 0. So it's a subsolution. So it's a subsolution is okay for all the arguments we've done so far. So you apply the first De Giorgi lemma, and you get that it's greater than an L infinity norm of G on the smaller ball squared with a constant. Okay, so L infinity norm controlled by L2 norm. That's the first De Giorgi lemma. We just lose on the side of the ball. You follow all the argument and you arrive at that. But now the L infinity norm on the ball 1/2 is exactly equal, you just calculate it, is exactly equal to the log of inf of f on the ball 1/2 plus delta over 1 plus delta. So we've proved that, let's forget that, these are constants if you want. We could track how everything depends on everything. So we have a square, and here we don't have a square. And this is it. The argument of Kriskov is just to observe that you have a square here and you don't have a square here. So for instance, f touching 0 on the small ball is not allowed. You see why? Because this would behave like ln delta to the square. So by taking delta small enough, the left-hand side would always be bigger than the right-hand side. Now you know it's trig positive. By taking delta of the order of the inf, you obtain, I'm giving you the result, you obtain that f on the half ball is greater than some lambda strict positive, which is of the order constant exponential minus constant lambda square over mu. Okay, so you have lifted the minimum. This is the same lambda finally in the reduction of oscillation. Okay, so in fact, Kruskov goes further, but if you combine that with much more technical arguments about the spreading of the minimum, Kruskov can also lead to Harnack as well, following the same train of thought. So it's an alternative to Harnack. Okay, tomorrow I'll have to do parabolic and hyperbolic. So I'll leave a lot of...
So tomorrow, you do parabolic
and hypoelliptic, sorry. No, so not hyperbolic. Or maybe I'll just go directly to hypoelliptic to skip, yeah.
Are there any urgent questions before tomorrow? If not, maybe we can.
Yeah, maybe
sorry.
just a vague remark. Seems to me, I mean, this business of the universal inequality for the log. Isn't there some family of arguments for holomorphic or superharmonic functions where you argue, like, if you know that something is superharmonic, then the log is or something like this? I mean, I vaguely remember things like that I used in the for the maximum modulus principle for a holomorphic function.
I don't know, maybe, but I'm not sure, François. Maybe what you're thinking about, and it's definitely related to all the sort of ideas I was stewing in this lecture. Maybe what you refer to is the sort of inequality like that, Laplace of log of u, f, sorry, minus greater or less, greater, yeah, greater than constant over time. That's well, in the parabolic case, that's called Li-Yao.
Yeah, I mean, something like that. There exists variant value without time. You know, it's
yes,
used in the theory, but I don't have it from the top of my head. When you're discussing use proofs of the harmonic functions, things like this,
it might be.
So,
I mean,
you know, I mean, it seems to be another argument of the same type.
Yeah. Yeah, it uses that. I mean, I hope I used it twice. I hope I convince you that the new term you gain from the log is really the source of a lot of things. It's quadratic in a linear equation suddenly. You create some nonlinearity by changing the unknown. And yeah, it appears in... also, one thing maybe related to what you say, François, we're looking at equations for which we don't know the fundamental solution because of the rough coefficient. If you had a fundamental solution, you know, typically it would look like something like that. So logging it would be a very good way to detect the decay away from the diagonal. So that's one way to understand what we're doing here as well. And the Li-Yao makes it even clearer, but you have the log estimate. I don't know if there's something earlier than that historically, but I would credit the fundamental use of the log to Nash. At least it's heavily cited by by Moser, Kruskov. Even in the Aronson method, it talks a lot about Nash. So even if the proof of Nash is barely used for the Hölder regularity, the ideas in the proof have had an enormous influence.